Hello, my listener. My name is Mr. Kugonza, presenting to you the third lesson on current electricity. To all the senior 4 candidates, this is very important. I hope you will enjoy it. Ohm's law. The current flowing through a conductor at constant temperature is directly proportional to the potential difference across it. Potential difference refers to the work done to transfer a coulomb of charge from one point to another. So Ohm's law relates current and potential difference across a conductor. There are two types of conductors. There are those referred to as ohmic conductors and non-ohmic conductors. Conductors which obey Ohm's law are referred to as ohmic conductors, such as all metals, electrolytes such as copper sulfate solution with copper electrodes, and some other conductors. There are also conductors which do not obey Ohm's law, and these are referred to as non-ohmic conductors. These include semiconductor diodes, filament lamp, thermistor, dilute sulfuric acid with platinum electrodes. Ohm's law can be verified using an experiment, using apparatus which you see in this diagram. We have a plug key labeled K, we have a battery, we have an ammeter labeled A, we have a rheostat, a voltmeter, and a resistor. So the circuit is connected as shown in the diagram. So this is the procedure. After connecting the circuit, the plug key is inserted and the rheostat is adjusted so that a definite amount of current flows in the circuit. This is the value of this value of current is recorded. As the current flows through the unknown resistance, a potential difference is developed, which is read from the voltmeter. The rheostat is again adjusted to a different value of current, and the corresponding value of voltage is noted. The procedure is repeated for at least 5 or 6 readings of current, and the corresponding voltage is determined. The values are tabulated, indicating the corresponding readings of I and V. A graph of V against I is drawn. A straight line graph is obtained, which verifies Ohm's law. If we want to determine the resistance of the unknown resistance, we go on to determine the slope of that graph. The slope gives the resistance of the unknown resistance. So that is the procedure of verifying Ohm's law and also determining unknown resistance of a resistor. So this procedure can actually help us in 2 ways. One, to verify Ohm's law, and also to determine unknown resistance. Here we have some of the characteristic graphs of non-ohmic conductors. And then on the right-hand side, you see the graph, IV graph for ohmic conductors. So filament lamp, a gas discharge tube, thermionic diode, and semiconductor diode, all their characteristic IV graphs are represented here, as you can see on the left-hand side. The explanation of those graphs is beyond the scope of your study, so I will not go into the detail of explaining why current against voltage graph for each of those graphs looks like that. Or for each of those non-ohmic conductors looks like that. The resistance of a conductor is the ratio of the potential difference across it to the current flowing through it. Resistance is measured in a unit called the ohm, named after Ohm, the founder of Ohm's law. So the ohm is the resistance of a conductor through which a current of 1 ampere flows when the potential difference of 1 volt is applied to its ends. So that is the definition of ohm. Now, Ohm's law equation can be determined from the definition of resistance, since we've just said that resistance is the ratio of the potential difference across the ends of a conductor to the current flowing through it. So we can make an equation: resistance is equal to V, where V is the potential difference, divided by I, where I is the current. Hence we can write V is equal to IR. We can also express I in terms of V and R. So I is equal to V divided by R. So all three expressions, all three equations actually represent Ohm's law. So if you want R, you make it the subject. If it is V, you make V the subject. If it is I, make I the subject. On the right hand side, we can see a triangle that can be used to help us remember these three expressions. If you cover letter V with your finger, then you get I times R. If you cover letter I, you get V divided by R. And if you cover letter R, you get V over I. So those are different ways of determining the equation. So that is how you can remember those equations. That's a mnemonic, very useful mnemonic. Resistors. A good resistor, a good standard resistor, should not alter in value as time passes or as it ages, and it should not be affected by changes in temperature. Wires used for standard resistors are made from special alloys, and the two generally used being manganese and constantine. Now, let us look at how resistors can be arranged in an electrical circuit. There are two types of arrangement. One is referred to as the series arrangement, and another is the parallel arrangement of resistors. So if you have three resistors R1, R2, and R3 arranged in series and connected to a battery, a same current flows through all of them, and the potential difference is developed across each one of them. So since current is flowing through all, then we can find the potential difference across each one. The first one, V1 is equal to I times R1, V2 equal to I times R2, and V3 is equal to I times R3. When you add the potential differences across each of them, you get the potential difference of the battery, or the EMF of that battery. So V is equal to V1 plus V2 plus V3. That gives you V equal to I into R1 plus R2 plus R3. That is making factorizing. And then when you divide through by I, you get V over I equal to R1 plus R2 plus R3. But V over I is R. So the effective resistance is therefore equal to R1 plus R2 plus R3. So what this formula implies is that if we want to find the total resistance of a circuit, we simply add the individual resistances, and that is how we get the total external resistance in any circuit. When resistors are arranged in parallel, the current flowing through each of them differs, but they have the same potential difference. Since they are all connected to the same battery, V being the voltage of that battery, we can therefore find an expression for the effective resistance. So this time we'll look at the individual currents that flows through each of the resistors, I1, I2, and I3. I1 is V over R1, I2 is V over R2, I3 is V over R3. So those are the various currents, but the sum of the currents is equal to I, the current which is produced by the battery. So I is equal to I1 plus I2 plus I3. Again, when you add those three currents, you get V over R1 plus V over R2 plus V over R3. You get I equal to V into 1 over R1 plus 1 over R2 plus 1 over R3. But I over V is the same as 1 over R. Therefore, 1 over R, where R is the effective resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that gives us the expression for the effective resistance. If those resistors are just two of them, then you would remain with R1 over R is equal to 1 over R1 plus 1 over R2, which becomes R equal to R1, R2 over R1 plus R2 if which is the same as the product of the resistances divided by the sum of the resistances. So that is how you express the effective resistance for resistors in parallel. Cells can also be arranged in series or in parallel. When cells are arranged in series, the total EMF is the sum of the individual EMFs, and the total internal resistance is the sum of the individual internal resistances of the cells. When cells of equal EMF are arranged in parallel, the total EMF is the EMF of one cell, and the total internal resistance is obtained the same way as with resistors connected in parallel. So that is how we handle cells. The advantage of connecting cells in parallel is that there will be less drain on the cells since they share the total current. So, but then there is a precaution on cell usage. Cells should never be left connected in parallel, because if that is done, if one cell has a slightly greater EMF than the other, there will be a current which will circulate in the battery and the cells will become exhausted. So you should not leave cells connected in parallel. When cells are connected in series, a greater current is produced. So if you wish to obtain a much bigger current, then we need to connect cells in series. All right, this is the end of the lesson. Thank you very much for listening to me.